You know, in parasitology, sometimes just finding a parasite isn't quite enough. For the really critical research, for the tough diagnostic cases, we need live, viable organisms. So today, we're going to do a deep dive into a classic, and I mean truly indispensable tool that's built for exactly that, the Baermann Technique.
So here's how we're going to break it down. We'll start with why we even need a technique like this, the diagnostic dilemma. Then we'll get into the nitty-gritty of how the Baermann apparatus works, its magic. After that, we'll cover how to identify what you've actually caught, pit it against some other culture methods, and finally, figure out where it fits into a modern lab's workflow. All right, let's jump in.
Okay, so let's start with a really fundamental challenge in diagnostic parasitology. I mean, looking for eggs under a microscope is the absolute bedrock of what we do, right? But it has some pretty serious limitations that can really affect clinical decisions and even our research. So let me just pose a question that really gets to the heart of the problem. When you're looking down that microscope and you see a classic, textbook, strong-guile type egg, what crucial information are you completely missing? Well, the answer is you have no idea what species you're looking at. Just take a look at this. On the one hand, you have an egg from Nematode americanus, and on the other, one from Ancylostoma duodenale. To the naked eye, they're basically identical. You can't tell them apart. But here's the kicker. Ancylostoma is way more pathogenic, so a diagnosis that just says hookworm found is, well, it's incomplete. It's this exact problem, this morphological ambiguity, that forces us to find ways to look beyond just the egg.
And the other huge problem? It's sensitivity. And there is no better or scarier example than Strongyloides stercoralis, because the parasite sheds eggs and larvae so intermittently and often in low numbers, a single standard stool exam can miss the infection up to 70% of the time. Think about that. For a patient who's immunocompromised, that kind of false negative could literally be a death sentence. We just have to have methods that can amplify the signal when we're dealing with a low-level infection.
So, how in the world do we solve these problems of ambiguity and low sensitivity? Well, this is where the Baermann technique makes its entrance. And you have to understand, it's not just another concentration method. It's this really elegant solution designed for one specific purpose: to harvest living, motile larvae. And that is exactly what we need.
The apparatus itself it's just brilliantly simple. First, you take a large, fresh fecal sample, and let me tell you, using a large, fresh sample is absolutely key to getting good sensitivity. And you place it on a porous barrier, something like gauze. This whole thing is then set in warm water inside a collection vessel, which is usually a funnel. This setup is designed to encourage the larvae to actively migrate out of the sample, through that filter, and down into the water. Finally, they sink and get concentrated in a little collection chamber at the very bottom, making them super easy to recover.
So what's the secret sauce here?
Well, the first core principle is something called thermotropism. Using that tepid water, right around 37 degrees Celsius, isn't just to make a suspension. No, it's a powerful biological trigger. It basically kicks the larvae's metabolism into high gear, which ramps up their motility and makes them actively want to leave the cooler fecal mass and move toward the warmth. Now, once they're free and wiggling around in the water, the second principle takes over: gravitational sedimentation. It's just simple physics. These larvae are denser than water. They can't just swim around forever. So they passively sink down through the water column and collect neatly right at the bottom of the apparatus. It's this 1-2 punch of active migration followed by passive collection that makes the technique so incredibly effective. And this brings us to maybe the most crucial point of all. The Baermann technique is, in essence, a quality filter. Any larvae that are dead or just not motile, well, they can't escape the sample. They get left behind. So what you collect in the end is what we call a physiologically vetted sample. Only the living, kicking organisms make it through. And that is a huge, huge advantage over methods like formalin ethyl acetate concentration, which just scoop up everything, dead or alive. Of course, successfully harvesting the larvae is only half the battle. I mean, if you can't accurately identify what you've caught, the whole procedure was kind of pointless, right? This next step takes a really keen eye and a solid understanding of larval morphology.
Okay, so when we're looking at these infective L3 larvae that we've recovered from the culture, there are two features that are absolutely critical for telling the most common human pathogens apart. First thing, look at the tail. Strongyloides has a very distinctive notched or forked tail. Hookworm larvae, on the other hand, have a sharply pointed tail. It's a dead giveaway. Second, you have to check the ratio of the esophagus to the intestine. In strongyloids, the esophagus is super long, about half the length of the body, giving you a 1-to-1 ratio at the intestine. In hookworms, it's much, much shorter, closer to a 1-to-4 ratio. Get those two down and you're golden.
Now, the Baermann technique isn't the only culture method out there. So how does it actually stack up against the other major players in the field? Let's put it head-to-head with agar plate culture and the Harada-Mori technique. When it comes to detecting Strongyloides stercoralis, the numbers are crystal clear. Agar plate culture, or APC, is the undisputed champion. The published sensitivity rates are phenomenal, pushing 95%, sometimes even higher. The Baermann is a very strong silver medalist, often landing right around 80%. And then you have the Harada-Mori technique, which, while it's simple, really lags behind, with sensitivity that can be as low as 28%. So if you look at the bigger picture, you can really start to see the trade-offs. Harada-Mori is super simple, very cheap, but the sensitivity is low. And, this is a big one, it carries a high biosafety risk. Why? Because infective strongyloids larvae are famous for migrating up the filter paper, which creates a direct skin penetration hazard right near the top of the tube. Not good. APC gives you the best sensitivity, no question, but it's complex. You need an autoclave, you need an incubator. The Baermann really sits in a nice sweet spot, high sensitivity, moderate complexity, and a much more manageable risk profile. So, that brings us to the big question. In an age that is just dominated by molecular diagnostics, where does a classical technique like the Baermann even fit in? Well, its role isn't going away. It's actually becoming more specialized, and in some ways, more important than ever. The key thing to understand is that PCR and culture are answering fundamentally different questions. PCR is a presence or absence test. It's fantastic at telling you yes or no, is this parasite's DNA in my sample? It's incredibly sensitive, incredibly specific. But culture answers a functional question. It asks, can we get viable, living organisms out of this sample? And that is precisely why culture is still indispensable. You can't run a functional assay on a snippet of DNA. For critical jobs, like monitoring for anthelmintic resistance, you need live larvae. In something called a larval development test, or LDT, we literally expose these cultured larvae to different drugs to see if they can survive. That's a question that PCR just cannot answer, and it's absolutely essential for guiding treatment strategies for both people and animals. So for any lab managers out there, the choice really becomes a strategic one, and it all depends on your goal. If your number one absolute priority is getting maximum sensitivity for strongyloids, and you've got the incubator and autoclave, then APC is your answer. If you need live larvae for resistance testing, or maybe you're diagnosing lungworm in animals, the Baermann is your gold standard, hands down. And if you're in a very resource-limited setting and you're just trying to speciate hookworms, Harada-Mori is a workable option. You just have to be very careful. And finally, look, we cannot overstate the importance of safety. Fecal culture is unique because your whole goal is to concentrate live, host-seeking, infective organisms. This is a living risk. All this work absolutely must be done under biosafety level 2 conditions. That means every sample is treated as infectious. It means proper PPE, gloves, lab coat, and crucially, it means using forceps, never your bare hands, to handle things like filter paper. When you're done, everything has to be decontaminated, ideally by autoclaving to completely neutralize that threat. So we'll end on this thought. Molecular tools, they're incredibly powerful, but they don't tell the whole biological story. The ability to culture and to work with living parasites is a unique and vital capability. So the challenge, and really the opportunity, for the modern lab is to figure out how to intelligently integrate these techniques, to use them together to answer the complex biological questions that molecules alone never will. Thanks so much for joining me.